Okay, is it working? It's, do you have the sound or yours?
You want it off?
Yeah, you don't have, okay,
Yes,
good.
yes.
No, it's working. Okay, okay, so good morning to everybody and welcome to the Friday colloquium of IAP. It's our great pleasure to have today Andy Fabian from Cambridge, UK, as everybody knows. And I took some notes here. I don't want to be too long because they're going to explain everything that Andy did in his life. I mean, I would need about an hour or so. So it's my great pleasure to welcome you here at IAP. And I think many of you certainly know Andy and have read one of his many papers. So I just want to make a very brief introduction. Andy is a Royal Society professor at the Institute of Astronomy in Cambridge. Was from 1982 to 2013. Was the director of this institute for also a long time, 5 years, I think, and then served as president of the Royal Astronomical Society as well from 2008 to 2010. On top of that, he was also, I think, discovered this morning, editor-in-chief of monthly notices for many years. So his main areas of research have been centered on the study of galaxy clusters, active galactic nuclei, black holes, and X-ray astronomy, where he made some fundamental discoveries. And all that is described in an astounding number of papers. That is about 1,350 or so. And Andy told me this morning that since he's retired, even writes more papers than in the past. So I'm looking forward to the next ones. And he has been awarded as well, based on his many activities, amongst other, the gold medal of the Royal Astronomical Society and the Kavli Prize for Astrophysics. So today, Andy is going to present recent results and research and overview of hidden cooling flows in clusters and groups of galaxies. So the floor is yours, Andy, and thanks again.
Is it on now? Yeah. Okay. So I want to talk about hidden cooling flows in clusters of galaxies. I've been involved in cooling flows in clusters of galaxies for a very long time, and I've gone back to them in my retirement. And I just want to start off with this beautiful HST image of the center of the Centaurus cluster of galaxies, which is one of the nearby clusters of galaxies. And this HST image is part of what it's all about. This should be now cycling to the next one, but it isn't. Never mind. Oh dear. It was working earlier. It's supposed to go to the next slide, and is it doing it? It's not doing anything. Oh dear. Any idea? This was, it did work earlier. No, it doesn't feel particularly hot.
Can you just stop the chair and restart?
Yeah, sorry about this.
You share again.
Yeah. And we'll see if it's
yes.
Good. Yes. I'm sorry about that. So for those of you who don't, I'm going to assume some of you know nothing at all about clusters of galaxies. They're the largest agglomerations of matter in the universe that are gravitationally bound. They can be up to 10 to the 15 or more solar masses, and they contain a large amount of hot gas. In fact, most of the baryons in a cluster of galaxies lie in the hot gas, not in the stars in the galaxy, not in the stars in the galaxies in the cluster. And there are two classes of clusters, according to me. That is, they're the cool core ones and the non-cool core. The cool core ones, this is now X-ray surface brightness. That's the Y, the Z-axis, and X and Y are spatial dimensions, plus or minus 1 megaparsec. So what this is showing you is if you look at the X-ray surface brightness from clusters of galaxies, the cluster like Abell 478, it's highly peaked in the center, and ones like Coma cluster are not peaked, they're sort of blunt in the middle, okay? That is because we think two of these have collided together and made one of those. But I'm not into merging clusters at this stage. I'm thinking about these ones where they've got this enormous peak in surface brightness. And the reason is the gas gets cooler and cooler as you go into the core, the center of the cluster. And as the temperature goes down, the density has to go up so that the pressure, NT, is able to support the weight of all the gas above. So as you go deeper into it, the temperature goes down, the density goes up, the surface brightness is proportional to n squared because it's Bremsstrahlung principally giving the X radiation. So therefore we get a very strong peak. From the X-ray data, you can work out what the cooling time of the gas is as a function of radius. And the cooling time is trivial. It's just the thermal time, the thermal energy. And you've got the luminosity, and there's virtually no bolometric correction because we're seeing the X-rays coming out. It's just due to the emission of the X-rays we see. So we can work out the cooling time as a function of radius. And this is work from a student of mine some years ago. And you can see that we get much the same picture from this. In many of these clusters, the cooling time drops below 1 billion years, and near to within a kiloparsec or so, it's dropping lower than 10 to the 8 years. So this radiative cooling time dropping inside the cluster suggests that something's going on. And within about the inner 50 to 100 kiloparsecs of the cluster, the cooling time is less than the age of the cluster, which is around half a Hubble time or so. So therefore, something must be happening. And we think that what is happening is it's losing energy from the center. The gas is losing energy through radiation, and therefore it's slumping inwards. And we call that process a cooling flow. Basically, it's losing energy, so it's moving inwards. And what happens to it in the center, that's what I'm about to talk about. And this was first thought about in the 1970s. Susan Lee was the first one, I think, in the early 70s to point out the cooling time in clusters of galaxies was less than a Hubble time. And then a bit later in the 70s, Cowie and Binney and Paul Nelson and myself came up with the models for cooling flows. And we then studied them in many clusters. The big problem arose around 2000 with the launch of XMM and also the Chandra satellites, where the XMM carried reflection grating spectrometers, a pair of them, and was able to give high resolution, X-ray high resolution spectra of the centers of these cool core clusters. And this is one of them, 2AO335. Don't worry any more about it. You can see the data. This is plotted against wavelength. And so 1 keV corresponds to 12.4 angstrom, so about there. And what we can see from the data is that curve, and the prediction of a cooling flow model is that there should be all of these lines, which we see down to a certain energy or wavelength. And then this is what the model would do as the gas cools below about 1 keV. We expect to see strong lines of iron 17. These are the brightest X-ray lines from the sun, so it's all familiar physics. These lines are not strong. It says missing, but you can see they're there, but not very strong. These lines are weak, and they indicate gas at a temperature about 0.5 keV, and we don't see them at the strength they should be. And there were several papers came out around 2001 saying, hey, we don't see any of this. these cooling flows don't exist. The spectra basically imply that less than 10% of the cooling rate that you would expect for a full cooling flow is actually happening. It looks like the gas is cooling down to a half or a third of the outer temperature. This idea has a problem in as much as the gas would accumulate if it just went down to a certain temperature. We don't see vast accumulations. You just don't see it. So what happens to this? Basically, people lost interest in the idea of cooling flows at this time. And I didn't lose interest, but kept on worrying about this problem. And I've continued to worry about it ever since. I had a student a few years ago look at the RGS spectra of many clusters of galaxies and look at the fraction of them that show significant cooling. And in fact, most of them show most of them show a cooling rate below a keV of the cooler gas, the soft X-ray emitting gas, which is less than 10% of what you would expect from what we call a simple cooling flow. And the simple cooling flow is just taking the gas mass within, say, some fiducial radius, define where the cooling time is, say, 3 gigayears, or you could take 7 gigayears, whatever, and you just divide the two, and that gives you a cooling rate. And basically, most of them are not doing this. So this is where we are. And when he came out with his results, I've spent quite a lot of time worrying about this, because it seems weird. How on earth can this gas cooling down so in towards the center of the cluster? What's going on to prevent it from cooling any further? What had happened in the meantime, and around when the RGS data first were being produced, was also Chandra X-ray telescope was launched the same year, 1999, and that was showing these spectacular images of clusters, showing these cavities or bubbles in the middle of the clusters. This is my picture. I call it my picture. I was a PI of the data of the Perseus cluster, which is the brightest extended X-ray source in the extragalactic sky. And here's the nucleus 3C84. And you can see the bubbles above and below, and then bubbles out here. And basically, the jets from the AGN are blowing bubbles in the cluster, and those bubbles are going out. They're becoming buoyant and floating upwards in the cluster. And there they are, a pair of old bubbles. And you can see that there's something going on with blowing these bubbles, because that's a shock, and that shock runs all the way around here. And so it's dumping energy into the surrounding gas, and so it's heating up. And so we've got the idea of AGN feedback. The AGN here is feeding energy back into the intracluster gas, heating it up and stopping it cooling. So this is the reason cooling flows are not what we thought they were. It's due to the bubbling that's taking place from the AGN in the center. And this from there to there, from there to there, is about 80 kiloparsecs. So this is AGN feedback demonstrated on a large scale where it's feeding energy back. So maybe that's what's going on at the center, where the cooling times get short and we don't see this iron-17 emission. Maybe what's going on is it's AGN feedback that's stopping it. But I was still worried about this because of the fact it seems like fine tuning. How on earth do you actually tune it so you don't get any emission? Because you'd expect sometimes with this messy AGN at the center, how does it know to produce just enough emission at that radius to stop the gas at that radius cooling? It sounds a bit as though we've got magic. So I've continued to worry about it. These are they're called cavities there, I called them bubbles just now, but you get the idea. And many of these clusters show these features. That's Perseus again, but these are other clusters with bubbles. And where we see bubbles, we can actually work out the power in the bubbles by what we do is we know from X-ray emission what the pressure distribution is in the hot gas. And if we've got a cavity or a bubble, we know the pressure that there must be inside it if it's in pressure equilibrium. And therefore, we know what the energy content is, and so we know the volume, so we therefore get the energy in these bubbles, and we can work out a rate at which they're being formed, because I think this is a bit like a fish tank aerator. You're blowing bubbles sort of regularly. You can work out the rate at which that's happening, and that gives you a power, and that's what's on that axis. The amount of cooling taking place, which we can measure from the X-ray emission from the cluster, we can compare the two, and that's a pretty good correlation for an astronomer, I think. But if you look in detail, you'll think, gosh, there's two orders of magnitude spread there, but so it's not such a good correlation, but at least it's indicative. So homing in on Centaurus, which was the cluster I showed you right at the start, this is what has pushed me all the time, and that is working out the cooling rate of gas from RGS data. It just seems to drop inwards down to zero. It's 30 or 40 solar masses per year out there. This is also going to be temperature going down, means going towards the center. This means there's 30 or 40 solar masses a year cooling out there, dwindles all the way to zero. And all the feedback seems continuous and gentle. It seems like fine-tuning to me if there's heat being put in. And I've been asking, can this complete decline in the M dot, I call M dot, that's the mass cooling rate, be explained by photoelectric absorption of the soft X-ray emission by cold gas? And so then I'm looking about this, maybe it's all to do with cold gas. And then I'll jump back some decades, more than 30 years now, to papers like this, where we announced the discovery of large amounts of cold X-ray absorbing gas in cooling flows, because this is not a small effect. You don't need the RGS to show you there's a lack of soft X-rays. You just need any old X-ray detector, it's showing it. And we first saw it with, for example, the Einstein Observatory solid-state spectrometer and with Ginga. That's just a proportional counter, a Japanese satellite. So that's an annual review article I did back in 1994. So we thought there was a lot of absorption going on. And right up until 2001, that's the last paper that was written on absorption in cooling flows by Steve Allen. And what happened beyond that, most of us jumped ship, including myself. So I'm guilty as well. We jumped ship and assumed that what was going on was feedback. Feedback was what was driving it. So, and the rest of the community also love to go there because there's a big problem with cooling flows if they happen at the rates I'm going to tell you they happen at. So what I'm doing, and I've gone and done this myself, the spectral analyses I'm going to show you have all been done by me because I don't have any students to do that anymore, no more postdocs and so forth. It's just me. But let's imagine a cooling flow takes place. Gas cools and cools and cools. What happens to the gas once it's cooled? You've got cold gas. And imagine a bit of turbulence. I'm waving my hands. So wave your hands a bit, and the cooling takes place with immense, muddled up with the cool gas. And so the cool gas that's there is going to absorb the soft X-ray emission from the cooling gas. So that's what a hidden cooling flow is. I thought of calling them absorbed cooling flows, but calling them ACFs, which are my initials, sounds a bit pretentious. So I'm calling it HCF, which is a hidden cooling flow, okay? So I think we need to reconsider absorption in cooling flows. And I'm going to use a multi-layer intrinsic absorption model that we first used back in '97. And of course, there's got to be energy conservation. Where does the absorbed energy go? It gets radiated out mainly with dust in the far infrared. Now, this is what I'm thinking about in terms of the observers over here. And this is this multi-layer cooling flow. The observer's way on the left. This is galactic absorption from our own galaxy. And then this is the multi-layer gas. So there's emission, absorption, emission, absorption, emission, absorption. And if you think about it, the emission you see is the result of a geometric series, because each of these emission things is seeing progressively more absorption. And when you work out that series, you can end up with the flux that we see should equal the total flux emitted by the layer multiplied by this stuff here, that's the total column density through the cloud, and that's the relevant cross-section, which is a function of energy. So we get that. So this is what happens. So this, if we go here, and this is against wavelength, this is a spectrum coming down here where basically the cooling flow is being truncated, and the red one is a hidden cooling flow where we've got absorption on it. And what the absorption is doing is pulling the lower energy, longer wavelength radiation is struggling more to get out. And another way of looking at it is this is a cooling flow spectrum. This is now against energy. So the x-axis has been switched around. So this is the total energy from just a model cooling flow. And this is what happens if you just put a sheet in front of it with absorption. It cuts off like that. But if you've got these interleaved emission, absorption, you end up with this red curve. And that's the hidden cooling flow spectrum I'm going to fit the data. Now, it turns out over the last 20 years, every time XMM looks at a cluster, it makes an RGS spectrum, or makes two actually, because XMM has got 3 X-ray mirrors, two of which half the aperture is used for reflection grating spectrometers that I'm not going to go into in any detail, but they are gratings. Being a dispersive spectrometer, you can't make sort of good images with them, but as long as your emission is fairly peaked, which it is in the cool core cluster, you can get a spectrum out of it without contamination from everything else. So this is the spectrum of Centaurus here. Looks terribly complicated. And this is what I get for fitting the hidden cooling flow model. And this is the mass cooling rate versus column density, the total column density in the cooling flow. And you can see an isolated region emerges, and basically I get a cooling flow of 15 or so solar masses per year. With Perseus, and this is now log this scale so I can show the intrinsic cooling flow. The intrinsic cooling flow is that faint dash thing there, and I get around 80 solar masses per year. So this, if there was no feedback in the rest of the cluster, would be more like 400 or 500 solar masses per year. But I think AGN feedback is working, cutting it down. It's doing the hard work, cuts it down by a factor of 3 to 4. And then what's happening at the center is most of the cooling taking place in the center is hidden in this way. And with Centaurus, you remember I showed you it at 30 and it drops down to the order 0. It's actually going along at around 15. And where does the emission come out? Well, fortunately, we've got Herschel observations of Centaurus and of Perseus. And the Herschel observations show this nice peak here in the far infrared from hot dust. And there it is also in Perseus. There's a lot else going on in Perseus, but there's a lot there. We can even image it in Perseus. So it comes out in the far infrared. And I'll show you later that things add up. But then we have to confront the other problem with cooling flows. And that is, if we have vast amounts of gas cooling, it's going to accumulate as cold gas. And what happens to it? Do we accumulate too much cold gas? What I'm saying is that in the Centaurus cluster, it's going to, in 1 gig a year, accumulate 1.5 times 10 to the 10 solar masses of cold gas. Now, ALMA shows us around 10 to the 8 solar masses of cold gas in the middle of Centaurus. That's a mismatch by a factor of 100. Perseus, which Philippe Salome and others have looked at in great detail, find a very large amount, 5 times 10 to the 10 solar masses in Perseus. But that's more than produced in just 1 billion years. It's the accumulation of gas. And I want to now talk about that in some detail, because some of you are experts in cold gas, and we can squabble about it. What is too much cold gas? We see some, but there's not enough. Maybe there's a lot more that we don't see. Maybe ALMA doesn't show us everything, and IRAM as well, because IRAM is what Philippe used to study Perseus. Perhaps there's much more in the form of ultra-cold clouds. Also, the bubble shocks, the bubbling in the middle, maybe that drags gas outwards, regulating the total amount of gas. So the cool gas, gas cools down, but it's being dragged outwards by all of that bubbling process I showed you earlier. And also, maybe it does cool down and it forms low mass stars, because high gas pressure lowers the gene's mass. Now, if we have an experts here on star formation, they'll say the gene's mass doesn't tell you what is going on in star formation, but it has something to do with it. And I would say that if you compare these objects, where the gas pressure at the center of these objects is of the order of NT, is around 10 to the 7. NT, that's much, much higher than in the interstellar medium. It's around 10 to the 7 in these objects. Then it lowers the gene's mass, and maybe we get lots of low mass stars. And we come in talking about bottom heavy IMFs and things. This was first discussed by Mike Dura in 1977. I wrote a paper with Claude Canizares and others in 82, and Gary Furland in 94. So it's something around. But there are these bottom heavy IMFs common in elliptical galaxies, and even M87, as Alderman Auger found and published recently. So I'm now going to look at the cold gas. This is now the Perseus cluster, my favorite cluster. This is the Perseus cluster. This is NGC 1275. You can see there's something funny about this. These are the filaments of NGC 1275. Let's go forward. This is HST image of 1275 and in H alpha. And I think it's pretty spectacular. Of course, if this was at redshift 5, everybody would be really excited about it, but it's just next door, so nobody's very interested in it. I mean, honestly, it's very difficult to get more observations of this because, you know, it's nearby. Anyway, the other thing to point out, the filaments, the optical emission from these filaments, I'm showing you H alpha, but if you look at the whole spectrum, the excitation of them is unlike anything in the galaxy, apart from the Crab Nebula. And I'll come to that in a minute. Is it due to energetic particles or irradiation by absorbed soft X-ray emission? That sounds interesting, doesn't it? And Paulez, who is from Paris, and I had others, Francoise and Philippe were involved, did some work on this a couple of years ago. The H alpha is like this. This is warm molecular hydrogen. These filaments are not just atomic, they're molecular. And Philippe showed spectacularly back in 2006 that these things, wherever you look, these filaments are molecular, and came up with this total mass here of 5 times 10 to the 10. And I'm going to tell you, I think that's an underestimate. We can all squabble about that. And these are just other examples of such objects. That's Perseus without the pretty picture on, because it's filaments. Some of them are very filamentary, and some of them even hydrogen Hydra A is a rotating disk, so you can go across. And this is from Olivares, Centaurus, and some other things as we go across like that, just showing you the H-alpha emission in purple, and the contours show you the CO emission. And this, look how spectacular that is. That's 14 kiloparsecs across in terms of the whole size of this object. So briefly from Gary Furland, who we collaborated with on this work, this was his contribution. Looking at the emission from coal gas, we just looked at it and what is the cooling time of gas when it's cold, if it's 50 K? What's the cooling time? The cooling time of that gas is very short, about 10 years. And even to get it down to 5 K, the cooling time is only 30 years, okay? So in order to have the gas at the temperature that most of people think it's at, you've got to keep heating it. And how is it being heated? And this is just Gary's calculation of the, and he's got the density there at 10 to the 6.5. These are the relevant cooling lines that he was using there. And he's taking basically ISM properties, and there's galactic cosmic rays in this calculation. And then just across to the Crab Nebula, which is the most similar object to this in terms of pressure, it's in our galaxy, then it has all these knots in it. And these knots, we believe, have formed since the explosion, and some of them are full of dust. And these dusty knots may well have formed the dust recently. And it was looked at with IRAM in work led by Al Wooten, and you can see carbon monoxide was easy to see. And this is the nearest kind of object which is going to be similar to the material that we're looking at in the center of the cooling flows. In terms of dragging matter out, this is showing you Chandra images of Centaurus cluster, where this is temperature, and where the temperature gets lower, the lower the temperature, the more it goes towards black. So it's the center of the cluster. The metallicity goes up to about solar and then drops down to 0.2 right in the center. So that may be telling you that gas is being pulled outwards. The dusty cold gas is being dragged outwards, but that's early days with that kind of thing. So what I've talked about so far is the first of 3 papers I've written on hidden cooling flows. This is now paper 2, which I'm going to run through very quickly. Basically, I've tidied up the spectra so they look neater. And you can see, all you need to notice is that many of these objects have got lots of nice emission lines. And as I said, whenever XMM looks at a cluster, it also makes RGS spectra. And most people never look at the RGS spectra because they're clearly very complicated and messy to look at and deal with. But this is a group, NGC 5044, and this is M dot versus column density in that fitting fraction. And this is roughly a covering fraction, is how much of the sensor is covered. Usually it's pretty close to 1. And you can see that's got a significant cooling flow of around 20. This is Abel 262. It's around 6. Abel 2052, it's around 10. I'm not going to show you too many of these. They are common. This is RX 1532 at redshift 3, and it's got an enormous cooling flow. This is Phoenix at redshift 0.6, even more enormous. This is looking at an elliptical galaxy in the Virgo cluster, M84, and it's got a cooling flow, hidden cooling flow, 1 to 2 solar masses per year. So they're everywhere. And you can see the iron 17 lines in these objects. And I'm stunned that most people have, including myself, in the past, have fitted the spectra from these objects, assuming no additional absorption. And yet these are taken from the literature, HST images of the centers of some of the galaxy clusters I've talked about. So there's NGC 5044, 262, 2052, CIRSIC 159. They're all full of dusty gas. So there is lots of dusty gas at the centers of these things. So certainly we should not fit them without including absorption. And it's not an enormous amount of absorbing gas that you need to use in order to get a hidden cooling flow. Now, paper 3, I've added in M87. Going further out from us, the next cluster is the Fornax cluster with the main galaxy is NGC 1399. You can see it's got a nice emission spectrum, and it's got a few solar mass per year cooling flow. NGC 5813 and 5846 are both in, it's called the 5846 group, and this is just to the side of it. They're same redshift, but they both have cooling flows in them. And then to finish off, I want to just show you this object. This object is fascinating, and I think it's going to become more and more interesting to everybody. It's Markarian 1216. It's a red nugget. It's at a distance of 94 megaparsecs away. Red nuggets were found by Daddy and others, and other people have followed on with that about 15 to 20 years ago. And they appear to be remnants of the first galaxies formed. They basically appear to be a collapsed core with a very small effective radius, with very little rest of the galaxy to them. And they appear to be not uncommon at redshift 2. But then people started to find them around about locally to us in about 10 years ago. Anna Ferrer Matter found some, including Markarian 1216, which is this galaxy. And that's what it looks like in X-rays. Now, it was Norbert Werner who went and got the X-ray image of this and followed it up. But its spectrum, I don't think he looked at the RGS spectrum. The spectrum of it is full of these strong lines. The iron 17 lines are this line and that line, those 15 and 17 angstrom lines. So they're very strong. And this thing has a cooling flow of it's almost 10 solar masses per year. So this is nearby, a remnant of an early galaxy. There's other work that suggests that it's got a very high mass concentration. There's a lot of dark matter in the galaxy itself. And that dark matter, I reckon, could be low mass stars, as well as whatever dark matter is. And it's very interesting that it's got one of these hidden cooling flows in. And then this is redshift 3, Zwicky 3146, another enormous hidden cooling flow. And I know you don't want to look at an enormous table, but I've got a table here with all the absorbed luminosities. This is the luminosity that's been absorbed. This is where I can find it, the far infrared luminosity. And I assure you, all of those numbers are bigger than the corresponding number there, okay? So there's more than enough energy coming out in the far infrared to account for the hidden cooling flow. So there are no problems energetically. And this is just a very quick schematic image showing you M dot versus the object. These are the names down here, but you can see all the reds are below the black. The black are classical cooling flows. That's just a simple rate from imaging from work by Hudson, and red are the measured values that we get. Then the last little bit that intrigues me is if we have all this stuff that's cooled down in the centers of these galaxy clusters, and they've all got black holes in. And by the way, Janelle Walsh has found a 5 billion solar mass black hole in the middle of Markarian 1216. Won't some of it go in the black hole? Why is this black hole not really luminous? There's a lot of enormous amounts of cool gas down here. Well, how much of it accretes into the black hole? Now, imagine that what it's done is actually, under its own gravity, it's actually collapsed. They've become very cold clouds, which have then collapsed into substellar objects. Some of that could actually slump and fall into the black hole. And what you need to do to get it to do that are going to be gravitational torques, because you're not going to have an accretion disk viscosity. It's got to be gravitational torques. And I could tell you a little bit about this. I'm no expert, but lots of people have worked on this over the last 20 years. They're bars within bars, spiral waves, all sorts of things can help gas move, and objects, massive objects, move inwards in these things. Could this be why many of the most massive black holes are at the centers of clusters of galaxies? The most massive black hole I know about is Holm 15A, which is 40 billion solar masses, according to this paper here. And that's at the center of Abel 85. And Abel 85, I've already looked at, does have a hidden cooling flow in it as well. So this is also a way of making black holes more massive. Maybe this is a way of skipping over the Eddington limit with regard to making black holes massive, particularly if it happened at high redshift. I'm pointing at Martha, you see. Here's another way of making massive black holes. But the interesting thing is maybe this process of growing black holes is actually happening around us today. I don't know. That's a very speculative comment, but is it possible that some of these black holes at the centers of galaxy clusters are growing from the gas that's cooled down into them? A reminder of spiral waves. This is the center of the Centaurus cluster. This is HST image. My HST image of Centaurus, and you can see the black hole is actually here, and you can see it's got this sort of spiral feature around it. You can also see there's a lot of absorbing material or emitting material, but there's a lot of cold gas in this optical image around the center of the Centaurus cluster. That's just another representation of the same thing, that if you stare at that image, you can start to see things in it. Can you see some legs that come down? And you can sort of see wings that come out either side. I won't go any further with that, but anyway, these are two of the objects I've looked at in Hubble. Sorry, I'm not responsible for the Hubble images, but I've looked at the RGS spectra of them, and they both have enormous hidden cooling flows. These are redshift 0.35 and 0.36. These are the H-alpha emission images of the centers of the clusters, and you can see enormous. That's the scale, 25 kiloparsecs, and you can see enormous filaments on these objects. Something which, of course, if there are lots of absorbing clouds at the center of these clusters, is you would expect the nuclei of these objects to be absorbed. And many of the nuclei in these cool core objects, at least in the X-ray, are either intrinsically weak or absorbed in X-rays. We don't have good enough spectra to know quite what's going on, but they're consistent with having significant absorption. And looking with ALMA, Tom Rose and Francoise and myself and others, a group of us looking at the absorption from in CO. This is a couple of objects, again, that I've looked at, NGC 5044, and that's a group, and Abel 2597 is a well-known cluster. And you can see the emission here in CO, and you can also see absorption. And that is, there it is, yeah. And you can see it in that one there. So the red is 1 to 0, and the blue is 2 to 1. But you can see there are absorption features, and interestingly, these are redshifted, so falling in towards the center of the cluster. But we're trying to get more data on these, on other objects to see how common this phenomenon is. What is the future of the work that's here? Well, there's going to be a non-dispersive spectrometer, X-ray spectrometer, another micro. Is that back? Yeah, it is, sorry. The PRISM is hopefully going to be launched in August, and that is carrying a microcalorimeter. It's going to be a reflight of the calorimeter in Hitomi, which was lost in 2016, which got a nice image, nice spectrum of the Perseus cluster, showing the hot gas had a velocity of less than around 160 kilometers per second. This will be flying hopefully later this year. We'll look again at Perseus and many of the objects I've talked about, and they will get very detailed spectra over the same band, only a much broader band. They're able to look they can look away from the center of the cluster and not be confused by everything. So I think that the future for hidden cooling flows is going to be in terms of that work, and I'm hoping that it'll be the 4th time lucky, because you know it was the first time the microcalorimeter was launched, that the spacecraft didn't make it into orbit. The rocket motor fell apart. The second time there was a massive helium leak before they were able to use it, and that became the Suzaku mission. The third time, then it was Hitomi in 2016, and due to a mishap, it was set rotating and spinning, and it spun itself to bits. So let's hope that 4th time is going to be lucky for the microcalorimeter. Then there's Athena, which I would like to say is going to launch in the early 2030s, but it's ESA have decided to redesign it, redefine it, and it's likely to be launched much later. So I don't know quite when it's going to happen. And there's likely to be probe missions from the US. These are billion-dollar probes, one of which axis would be an arcsecond X-ray telescope with CCD resolution, but we'll be able to look at things like Centaurus in fantastic detail, and will be excellent for this. There's also another one called the Light Element Mapper, which would be able to do X-ray spectra of the soft X-rays and be very useful. So there's a competition going on, or is about to happen within the US between different X-ray missions that might launch in the early 2030s. So I'm going to give you my last slide. Mass cooling rates are actually several times more than unabsorbed estimates. Most of the absorbed energy comes out in the far infrared. Question is, ultra-cold clouds may exist. Implications for low mass star formation, brown dwarf formation. Is that where things are happening? The mass of cold gas is also controlled by bubble shocks and outflows. It's likely that there's a lot of cycling of gas in these regions. The inner few kiloparsecs of these cool cores are very complex and multi-phase, and we need lots more observations. The large range of relative densities and sizes challenges numerical simulations. most of which assume the region is optically thin. I've yet to find that there are millions of numerical simulations have been done over the last 20 years of clusters of galaxies. I have not found a single one which has included X-ray absorption. Naughty, naughty. Some fragments from the center may be swallowed whole by the central black hole while emitting little radiation. And all models and interpretation require cold absorption. So thanks for listening.
Well, thank you so much for this fascinating talk. I'm sure that there are many questions, and François is first.
I would have guessed that François was the question.
So thank you very much. And it's very beautiful and also a very appealing mechanism to hide cooling flow. So I like this cold accretion, of course, but I was worrying about the column density and filling factor, because you need cold clouds. In general, they are fragmented.
Yep.
And they are not filling the whole space in surface, very small. So in your model of several layers, do you take into account this small filling factor, and is it more efficient? Or?
Well, the actual model is very simple, and it assumes the emission and absorption are next to each other, okay? We've also got spectra of the filaments in Perseus. And I can fit that spectrum with one of these hidden cooling flow models, and it works and shows there could be happening in those. Okay, so somehow it's emission and absorption are right next to each other.
And
so
they have the same filling factor, emission and absorption.
Sorry,
the same filling factor in surface.
Yes,
that's a problem, because in general, cold clouds are small filling factor with respect to the emission. Yes. Yeah.
If we want to get absorption.
Yes.
With CO. Yeah, sure. No. Yeah.
So maybe it will be less absorption than you think if you have a covering medium.
I mean, what I need, for the beam that I have, when I say covering fraction is around 1, the covering fraction I mean there is the covering fraction of the soft X-ray emitting gas that is actually cooling. And it may be cooling in filaments and in special spots, okay? So it's that covering fraction it talks about, not the whole region, okay? I agree that with regard to the nucleus, if we want to have a lot of absorption, and at the moment, would you say it's a quarter of them have
a filling factor can be 10% or less.
Yeah. So that's for the center, and it may well be radially dependent, this covering fraction. I don't know. So when I've put on that plot, covering fraction, it's what I mean by that, it's not a physical thing. It's the ratio of unabsorbed cooling to absorbed cooling. Okay.
Okay.
Mostly this is really related because it's on the same figure, I think, or when you were presenting paper 2, you were showing many figures with m dot versus nh.
Yes.
And in some cases, I think Phoenix, for instance, there is the half of the region was so exactly. So my question is, and kind of related. So also the NH range on the x-axis was not enormous. I think it was linear, not logarithmic.
That's right, it's linear. Yeah.
Okay, so it's not very large numbers in terms of column density. So you don't need the very, very dense clouds. They are average density.
The NH doesn't tell you what the density is. It's a column density. Okay, yeah. So basically we need column densities of the order of 1 to 3 or so times 10 to the 22.
Yeah, which for me are relatively low. Small
yeah, sure.
And so going back to the first part, so the uncertainty being so large is caused by, is statistical, you need better spectra. What is the main reason for that?
I'm hoping that we will with better spectra, it may be with CRISM, improve on that. But if I just quickly go back to some of those, it's frozen again. Anyway, anyway, if we go back to them, you'll find that the ones that have enormous regions are the ones that have poor spectra. Yeah. So there's a direct connection between them. But basically, what we find where the spectra are poor, what I find is that basically you still need some absorption, but as soon as you put some absorption in, it's difficult to tell. It can be this much or that much. It doesn't matter. And you will have noticed that quite a lot of those contour plots were very sort of fragmented and messy. And that's because we're dealing with emission lines. The spectra are very complicated. And so that's what leads to the corrugations.
Thank you.
Thank you.
Thanks, Andy. That was wonderful. And so coming back to the talk you gave in '94 at Les Arcs in Morillon, I was talking to you about it. So
yes.
you were already talking about multi-phase gas in this cool core region. And so I have just a naive question, which is, you mentioned that, you see molecular hydrogen and you see H alpha. So how does conduction come in? Are the conduction times long enough that these things are stable, or is it that the bubbles are moving enough that they can collide and somehow avoid the conduction effects?
I think we have to switch off conduction altogether. So I don't know is the answer with regard to conductivity. In clusters of galaxies, I've been involved in some work where there are cold fronts seen in clusters of galaxies that should be wiped out very quickly, and the cold front, temperature contrast, and you see the length between them. It must be suppressed by a factor of 100 or so. So I think conductivity is highly suppressed. But, it depends upon where the magnetic field is and where it's going and so forth. So thanks for the question. But I would switch off conductivity.
Thanks.
Okay, thank you very much for this very nice talk. And I have a general and probably very naive question. Since we're speaking about flows, ordered or suborbital or subordered motions of gas, is it possible using X-ray spectra to measure velocities of different structures, substructures, filaments? Because I know that it was done for coma cluster a long time ago using Suzaku. And I have this question in general for all these nearby clusters that you had in your talk.
Yeah, thank you. For the hot gas, we can measure the velocities from the ion. In particular, that gives you the best answer. And so CRISM will actually be able to do that work. We did it only with the Perseus cluster, and we got 160. And in fact, it drops. There was later work of the same data, but analyzed it and found a lot of the regions were below 100, and there was a few regions up around 200. So we can, that should be redone and we get more work. But the hot gas in clusters of galaxies is not highly turbulent and has velocities that are 1 to 200 kilometers per second. That's great. With regard to the CO, of course, we have velocities from that, and people have done lots of wonderful work recently with H alpha emission, and an ex-student of mine, Julie Flaperchek-Larondo at Montreal, and her students have recently got some wonderful data from CFHT on the Perseus cluster, showing the velocity structure there. So the velocity structure is growing. It's going to be something we will learn more about. Unfortunately, of the inner kiloparsec, we don't know much. So that's for the future.
Hi, Andy, thank you. I have a question about the spatial resolution. Can you resolve the absorption, in particular in the Perseus cluster?
resolve the absorption spatially?
Yes.
No. The RGS has, because it's basically it's a dispersive spectrometer. You can trim it down a bit. We can go, down to an arc-minute, but we can't go below that in terms of getting spectra. So I'm afraid we can't do that. That's again, Prism won't do that because its spatial resolution is about 1.5 arc-minutes. So that's going to have to wait till Athena.
Hi, thank you very much for the nice talk. So you started from clustered with and without cool cores. And could you comment on what differentiates the two populations? And I'm wondering if there's any clue about the cooling flow to understand, between the two populations.
And I would say that cool core clusters make up around 40 to 50% of the population of clusters. And if you get sort of luminous groups, most of them are cool cores. Mergers, clusters like Coma, the Coma cluster has 2 giant galaxies at the center. And also there's a CD galaxy off down there. So it's probably had a merger, is taking part in a merger. It's a mess. And there are some merging clusters where we see a cool core being broken up. And I've worked on it, Abel 2146 that Helen Russell's done a lot of work on. And there's actually there is a cool core with H alpha emission on one side that's clearly being broken up. But I think that the non-cool cores are ones that have had a major merger. The cool core clusters tend to be very relaxed clusters, which have no sign of mergers, which is not to say that the central galaxy in them isn't somehow possibly wobbling around, which is another thing to be thrown into the mix.
There's a question from Johan Dubois on the Zoom, and the question is, are there indications that non-thermal processes like turbulence, cosmic rays are sufficient to balance cooling in the ICM?
Yeah,
so
thank you. Yeah.
Deactivating, yeah.
Turbulence has long been considered here.
Anyway, so
okay, with regard to the Hitomi result on the Perseus cluster, it turns out that the energy in turbulence is only 4% of the thermal energy of the core. And at the rate at which the luminosity of the core means it will only last, a few 100 million years if you were to rely on turbulence. So the turbulence has to have energy supplied into it. And I wrote a paper about this. You have to supply that energy at a rate which is around the sound speed. So you can't do it with the turbulent, assuming the turbulent motions are of the order of the velocities that we actually measure from the iron K line. And certainly those processes, turbulence, cosmic rays, and so forth, have been invoked. I've just pointed out, I've tackled the turbulence one. In terms of cosmic rays, there are certainly radio sources in the sensors of these clusters, so there must be cosmic rays. I struggle to see how they can make a close balance such as to make this m dot drop to 0 very smoothly. But people have written papers on cosmic ray heating.
Okay, thank you. Is there any? Oh, there's a question at the back there.
Thank you for the very nice talk. the far infrared emission, do we see where it's coming from? Is it more in the cluster?
In some cases, I showed you the Herschel image. I'm afraid I can't go back because it's frozen again. So with Herschel, we do have an image of where it's coming from. Generally, it's not resolved. And I think for most of these clusters, the Herschel, do you remember the resolution of it? Yeah, so I'm afraid it isn't good enough to do that, but there may be future far infrared emissions that will actually show us what's going on there, which will be very interesting.
Because I'm thinking which other sources it could come from.
Sorry?
I'm thinking which other sources it could come from. Of course, it would be galaxies, but could they account for it?
The infrared emission, what we did was look at the BCGs, the brightest cluster galaxies, and the emission is definitely coming from there, but we can't tell any, and we can tell it's coming from the centers of them, but we can't tell any more, other than Perseus, where it's clearly distributed like the H alpha emission.
Thank you.
Is there any other question in the room? Or if not, then I would like to thank again for your brief presentation. Thank you. That's it.
Good.